Okay, let's solve some problems. So say you have a boat and you want to analyze the force needed to pull the boat. So you'd first set up a free body diagram with all the forces represented. So notice we have each of the normals under the wheels and a weight represented at the center of gravity. And then we would set this equal to the kinetic diagram. So what we're interested in here mostly is this mass times the acceleration of g. Now, possibly we might want to, when we're solving the problem, sum moments about the point B, in which case we would want to know what the distance d was. But we might just sum moments about g and set that equal to 0. Either way, we establish an inertial coordinate system. Essentially, we're saying that this is our coordinate system here. Say this is our x direction, and this is probably going to be our y direction. Then the second step would be to draw our free body diagram, which we already did. And make sure you draw your kinetic diagram. And that's what I use to establish my x and y directions. Then you just simply apply 3 equations of motion. Three independent equations of motion. So forces in the x direction, forces in the y direction, then you sum moments about a point. Keep in mind that friction, if it pops up in your problem, friction opposes. So the force is drawn in opposition of the motion. All right, so let's look at an example. So we have a truck accelerating down the road, and there's a table or a desk sitting in the bed of the truck here, and the legs are positioned at B and A. Center of gravity of the desk is at G, and there is a coefficient of friction of 0.2 on this truck bed here between A and B. Okay, this thing weighs well, it has a mass, let's say, of 100 kilograms. So we want to find the maximum acceleration of the truck possible without it losing the desk, or without the desk starting to slide. So if the desk starts to slide, it's just going to continue to slide and it'll slide off. So let's draw a free body diagram of our desk. We're going to have a weight here, and that's 9.81 times 100 kilograms, or 981 newtons. We're going to have a normal at B and a normal at A. So now we got to figure out our friction, in which direction it points. So it's going to point either left or right, but which way? Well, if our truck is accelerating this way, that means relative to the truck direction, the desk would move in the opposite direction. So our friction should oppose that. And our friction is here. So this is the friction of B and our friction of A. Okay, that's it. Now let's do the same. draw the same picture, I guess, for our kinetic diagram. Here we have G, and now we have simply a mass times the acceleration of G in the x direction. We also have a y direction here, but so this will be my positive direction, but nothing's going on in the y direction. So let's apply our equations of motion and see if we can't solve this problem. So let's sum forces in the x direction. That equals mass times acceleration in the x direction. So summing forces in the x direction, we have 2 friction forces. So 0.2 times the normal at B plus 0.2 times the normal at A, and this equals mass times the acceleration, essentially of G in the x direction. And our mass actually is, let's throw it in here, 100 kilograms. All right, that's our first equation. Looks like we have 3 unknowns in it. So let's deal with that by creating some other equations. Let's sum forces in the y direction. Now there is no acceleration in the y direction, so this is going to equal 0. And then this equals the weight. Well, it equals the normal in B plus the normal A minus the weight, which is 981 newtons. All right, so there's equation number 2. So that's 2 unknowns in that equation. We can get this down to 2 unknowns up here, combination of that equation. So here we go to our third equation. Let's sum moments about G. Now, we've got no rotation. We're summing about the center of gravity, so there's no angular acceleration, so I alpha falls off too, and this just equals 0. So summing those moments then, pull the truck image down so we could see it. So we've got 0.2 distance times the normal of A times distance 0.75. So that is 1 friction force, and the other is at B is 0.2 times the normal at B times 0.75, the distance to the center of mass, and then we add to that the normal force of A times 0.9 minus the normal force of B times 0.9, and that's because we're going to say that as our clockwise. Not 0.9, but 0.6. The distance is different. And this equals 0. Well, okay, we have 2 unknowns in this equation, and so we can use 3 and 1, solve them simultaneously, and we'll end up with the normal of A equals 294 newtons, and the normal of B equals 687 newtons. Finally, we can plug these two back into equation 1 here and solve for acceleration. So acceleration of G equals 1.96 meters per second squared, and that's what we're looking for. So if we accelerate at least 1.96 meters per second squared, that's going to be the exact 0 point. Any acceleration above that, any infinitesimal acceleration above that, will result in the table sliding, and we'll lose it on the highway. Okay, let's solve this problem. Now, even though there's rotation occurring in this problem, this beam BD is experiencing curvilinear translation. Every point in this beam is moving with the exact same acceleration in the exact same direction. Now this problem, these links have no mass, and this beam has a mass of 100 kilograms. This suspended beam has a mass of 100 kilograms. Let's find the force in the rods at the instants shown when this is at 30 degrees. So here's our free body diagram for the beam. We've got two T's. Up here, the tension in B and the tension in D, and we've got the weight of the beam. So all this will equal this situation where we have a curvilinear path, and because of that we'll have an acceleration in the normal direction as shown here and an acceleration in the tangential direction as shown here. And now this just turns into a problem of trigonometry. Let's begin by summing moments about G this time. And again, G has, there is no rotation going on of this member BD, so there is no I alpha term. There is no alpha term. So when we sum moments, this is set equal to 0. So the first term is minus TB cosine of 30, so that's going to be essentially this component here times 0.04, and then we'll add to that the second term of TD cosine of 30 degrees times 0.4. Notice that this one is clockwise and this one will end up going counterclockwise. Let's next sum forces in the normal direction. So we'll end up with a TB, because this is in the positive direction, plus a TD. And then we have a component of the weight here. We have a component of the weight, 981 cosine of 30 degrees. And then all of this equals mass again, 100 kilograms, times our normal acceleration. Now, I forgot to point out that we do have an omega here of 6 rads per second. And we're going to need that because if we come down here to our equation here, we're looking for our acceleration in the normal direction. And if we look at one of these bars, say for example AB, we know that the acceleration in the normal direction points towards the point A, and so this acceleration is omega squared r, or 6 squared times 0.5, which results in 18 meters per second squared. Now, this is one point on our member here. If we look at point B, and all points on this have the same acceleration, so acceleration normal equals the acceleration of our center of mass in the normal direction, and that still equals 18 meters per second squared. Now this can be placed into here. So these two equations now only have unknowns of TB and TD, and we can solve both of equation 1 and equation 2 simultaneously. And we end up with 1.32 kilonewtons for each of those. We can further sum forces in the tangential direction and solve for acceleration of G if in the tangential direction if we want. And I'll just give you the answer there, but you can go ahead and do that by summing forces in the tangential direction.